Okay, good morning, one and all. So we are starting today the 17th session, 17th lecture in this EHV subject. So this is going to be the last lecture in the module number 2. So today we are going to finish the module number 2, and then we'll have a set of questions for module number 1 and module 2, whatever are important for IES and NSEM exam. So this will be an exhaustive question set. You can start preparing all these questions from my slides and the book. And also I will upload the OBA question, which you have to submit by Tuesday. So many of the students, those who are not attending, even everybody have to submit. So an instance will be created in Google Classroom. So there you have to upload the scanned document. And while you are writing the answer, write the answer. Question will be asked for 5 marks, but write the answer. Preparation should be for 10 marks, as you will write it in NSEM exam. So that is an instruction given online. So please adhere to that. So we have so far seen generally 4 motors, that is DC motor, we have seen induction motor. Induction motor actually are there for 2 types, single phase induction motor and 3-phase induction motor. But we have done 3-phase only because single phase induction motor is generally not used for vehicles. Single phase induction motor is used for all the household applications and all because they are low power device. But 3-phase induction motor is mainly is having a lot of industrial usage, and they are used in EVs as well. So we have seen DC motor control principle, induction motor control principle. Last day we have seen BLDC motor, that is brushless DC motor. We had found there that the rotor is connected with the permanent magnet itself, and it's a very unique kind of design where rotor is generally outside. So generally what we find is stator is outside and rotor rotates at the center of it. But BLDC motor is a unique kind of thing where we are finding that stator is kind of inside, it is getting all the 3-phase supply, and rotor is rotating outside. So rotor is just a metallic plate kind of a thing, and it was having permanent magnet connected with it. So that was BLDC motor. As the brush commutator arrangements are not there, it was having very high efficiency. And as brush commutator arrangement was not there, as well as the field coil was not there, because field coil is in a motor is used to produce the electromagnet. Because for motor operation, 2 things are required. One is the electric field, another is the magnetic field. So electric field we can connect directly to the rotor, as we did in case of DC motor, which is a conduction type motor, and magnetic field was being created from the same electric supply. But for BLDC motor, as it is PM BLDC, PM stands for permanent magnet. So a permanent magnet is there. That's why creation of magnetic field is not the responsibility of the electricity input. So that's why there is no field coil in BLDC motor. This is the main difference. And stator was given the supply. So we had seen there are 6 coils. So there are pulses, and video was shown to you. So the video is uploaded. You might have seen it. So regularly, one after another, coils were being energized in case of BLDC. The same kind of principle you will find in case of SRM drive also, which is our today's topic. So SRM stands for switched reluctance motor. It is almost having the same kind of principle as we had for BLDC motor, but with a little difference. So let us first find out what is a SRM drive and what is control. This is the last topic. If you can find the syllabus list from your module 2. So module 2 is mainly having 2 parts, as I told. First part is the SI and CI engine, that is the petrol engine and diesel engine. We have seen what is the difference between petrol engine and diesel engine, and then we have entered the field of electrical drives. So module 2 is all about generation of power which is required to drive a car. So for petrol and diesel, it was initial part. So which petrol and diesel is what is a kind of a mechanical or non-renewable kind of a thing, supply. But we have electrical drives are having a lot of advantages, and hence in case of electrical drives, the electrical motors are the main thing that generates the power. So what are the different types of electrical motors that we have seen? DC, AC. AC means induction, okay, and DC means conduction, and then BLDC, and finally we are seeing what is called as SRM drive. SRM stands for Switched Reluctance Motor. So in the book of Ehsani in page number 193, you will be finding all these details. But I have not taken much from Ehsani's book because they have gone too much into details of SRM for but you don't know SRM quite well. So my main aim in this lecture is not to go too much into electrical drive based SRM. My main aim is to tell you about SRM, that is switched reluctance motor, how it rotates, and what are the advantage, disadvantage, what is the working principle, and first thing, what is meant by reluctance and what is meant by switched reluctance. So again, it's we'll be finding there are three coils, and as we have done in case of BLDC, that one after another coil was being energized, the same thing will be done here. Okay. So I have not taken much from this book of Ehsani. So below it is given that from the book of Ehsani, page number 193, you can find out the detail, but I have not taken much. I have taken from two websites. Those I will be sharing with you. And self-learning topic, this is the last topic in module 2, which is said that DC motor operation and all. We have already done DC motor principle of operation. We have seen a video and how to control a DC motor. We have used chopper control. So all the things related to the self-learning topic is already done. So today's topic will be SRM drive. I think almost 30 people have joined. So we can start directly the topic now. First thing is, what is meant by reluctance? So reluctance is something which is equivalent to resistance in the magnetic circuit. So in magnetic circuit, the thing that flows in magnetic circuit is the flux. What flows in electric circuit, don't say it is current, it is actually electron. So electron is the flow in case of electric circuit, and flux lines is the flow in case of magnetic circuit. So whatever is the opposition to the flow of electron is called as resistance in electrical circuit, and whatever is the flow, what is the opposition given to the flow of flux is called as reluctance in the magnetic circuit. We have seen in the electric circuit that electric circuit or the electrons, they always try to flow through the least resistance path. So if I give you a resistor and if I keep in parallel with that one short circuit path, we have done it in networks. So we'll find that always the electrons would try to flow through the least resistance path, that is the short circuit. In case of magnetic circuit also the same thing happens. Whichever path is having less reluctance, through that path the flux lines would try to follow. Now reluctance is same as magnetic resistance. So flow is magnetic flux in case of magnetic circuit. In electric circuit it is flow of electron. Opposition to the electron flow is called as resistance. Opposition to the magnetic flux flow is called as reluctance. Now if I ask you that if there is air and if there is a ferromagnetic substance, which gives a higher resistance or higher reluctance to the magnetic flux, or which gives lower reluctance to the magnetic path? So exactly in the same line of electrical, you have to understand that if current tries to flow through metal or if current tries to flow through air, through which more resistance will be offered. Obviously, resistance offers very high resistance to the electricity flow or electron flow. In case of magnetic, also same thing. If the flux lines are supposed to flow through a ferromagnetic substance means iron, copper, nickel, all those things. Okay, in that case, it will be less. So resistance will be less when the flux are flowing through the ferromagnetic substances, and reluctance will be more if the flux lines are flowing through the air. Okay, so that's why we find that whenever the flux lines enters the air, it just blows out. So if it is flowing through a single channel, so if there is a metal path here, so through that metal path all the flux lines are flowing for magnet. Then suddenly between north pole and south pole there is a gap. So here is the north pole, here is the south pole, and he is a horseshoe kind of a magnet. So in the horseshoe kind of a magnet, all the flux lines are contained within the magnet. Okay, because it's a least reluctance path, so all the flux lines are concentrated within the magnet, but between north pole and south pole there is an air gap in between. What happens whenever the flux line flows through from the north pole to south pole? So from the north pole it comes out in the air, and in the air it fringes. Fringes means it is not concentrated like this, it just blows up. Okay, so it comes like this, then blows up again. When it entering the south pole, it again concentrates. So one factor you can find out in magnetic circuit, which is called as fringing, Fringing. So what is meant by magnetic fringing? So magnetic fringing is, if it's a horseshoe kind of a magnet, as long as the flux lines are within that ferromagnetic substance, that time it will be a concentrated path of the flux lines. And as soon as it comes out in the air, it just blows up. Okay, it becomes bigger. So there is a bulging kind of a thing. Okay, and again when it enters the ferromagnetic substance, again it is concentrated. So why that bulging thing happens when it is in the air? It happens because of reluctance, because air gives more reluctance to the magnetic path compared to ferromagnetic substance. So I think the concept of reluctance is clear to you. So simply you have to remember, reluctance is magnetic resistance and ferromagnetic substance gives very less reluctance and air gives very high reluctance. So it is said here, reluctance in magnetic circuit is equivalent to resistance in the electrical circuit. Reluctance in a magnetic circuit is the opposition to the flow of magnetic flux. And what is the equivalent to magnetic flux? Equivalent to magnetic flux in electrical circuit is flow of electron. Now here in the diagram it is said, it is shown. So in case of a switched reluctance motor, we will find the same thing. So this is a stator pole. So this is called salient feature. Salient means from the if this is circular kind of a body of the stator or rotor, suddenly from there is something protruding. So if this is the pole, so this pole suddenly comes below like this. So this is the this kind of thing is there, the stator core. From here suddenly there comes something below. Okay, that is this part, that is the stator pole part. So something protrudes at the output side. So that is called a salient pole. So there is a stator pole, and this is there is a already created MMF field, that is magnetic force field. That means there are some flux lines like this. And rotor pole is rotating. So rotor pole is also made of ferromagnetic substance. Stator pole is also made of ferromagnetic substance. Now you have to understand that this rotor is rotating in this case clockwise direction. Suppose rotor is rotating in the clockwise direction. Here stator pole is static. So whenever in the leftward diagram, so in this main diagram you can find there are four sets which are shown. Left side is highest reluctance path. Why? Because rotor pole and stator pole, they are misaligned. That means the flux lines are passing through the stator pole, and then the air gap between rotor pole and stator pole is quite big. In this case you find here in the leftward diagram, extreme left diagram. So there are four diagrams, four cases. So in the left side you are finding that between stator pole and rotor pole there is huge air gap. Huge air gap means this is the maximum reluctance case. Okay, rotor is rotating in the clockwise direction. So in the extreme left case, air gap between the stator and rotor is too high. That's why this is the maximum reluctance case. Now rotor is rotating. Rotor now comes to the right. You are finding that flux lines, more number of flux lines have concentrated between the stator and rotor. So between stator and rotor, the air gap is reducing. Then the third diagram, in this case, rotor has further come almost below to the stator pole. So you are finding increment in flux lines. So in the first case, there are two flux lines. In the second case, there are four flux lines. In the third case, you are finding almost six flux lines. So this is actually reluctance or magnetic resistance is reducing. And in the last case, you are finding that stator and rotor both are perfectly aligned. In this case, what you will find is this is called as least reluctance. That means resistance between the stator and rotor flux flow is minimum, because rotor and stator, they are perfectly aligned. So principle of switch reluctance motor is, whenever the rotor and stator pole are not aligned, it is the property of the rotor that it would try to align itself in such a way that the reluctance between stator and rotor would be minimum. So this is the basic principle of switch reluctance motor. I'll just repeat the same thing once again, that if initially the stator and rotor pole they are misaligned like this, so reluctance between the stator and rotor pole for the flow of flux is very high. In that case, the rotor would try to adjust itself in such a way that the rotor and stator reluctance, that is magnetic path reluctance, is least. That means what would happen? The rotor would automatically rotate towards the stator in such a way that this kind of rotor stator alignment would be achieved. So that rotor and stator, they are coming exactly in front of each other, and hence the least reluctance is being obtained for the magnetic flux which are flowing from the stator to the rotor. But the problem is, as the rotor is having inertia, it cannot stay it like this forever, because it is a rotating substance, so it cannot stay it here. So this rotor again will be shifted forward by means of inertia. So whichever rotor is there before it in the left side, again that will be having this kind of a alignment, and automatically it will align itself like this. So this process will keep on going on, and the rotor will start rotating. So I'll show you a video, 7 to 10 minutes video. You would understand exactly how the switch reluctance motor basically works. So switch reluctance motor works based on the principle of variable reluctance principle. Now this SRM is also called as VRM, that is variable reluctance motor. Both are same. Okay, so variable reluctance principle. Why variable reluctance? Because if stator and rotor are misaligned, reluctance is very high, max. If rotor and stator are perfectly aligned, reluctance is less. Okay, so between that, reluctance is medium. So as the reluctance between stator and rotor is changing, this SRM is also called as a VRM. So switch reluctance motor works based on the variable reluctance principle. The rotating magnetic field is created with the help of power electronic switching circuit. So there is an alignment. So I will show you the video. You will understand that continuously we are changing the pole of the stator, and we are creating so that carrot principle, as we had shown you yesterday in case of BLDC, that you are just changing the pole in front of that rotor pole, so that rotor will go and try to catch that opposite pole, because N pole attracts S pole and N pole repels N pole. Same pole repels and opposite pole attracts. So as soon as one rotor has come in front of one stator pole, exactly at that time, this upper rotor pole will make the same pole just by changing the electronics. Hence, the rotor pole will be repelled, and just the next stator pole we will make opposite pole, so that this rotor pole will be attracted towards that. So initially it is attracted. As soon as the least reluctance occurs, we will change the stator pole to the same pole. So this will do two things, and just immediately next pole to the opposite pole. So it will happen two things. That is, this pole and this pole has become same pole now. After it has reached this, now the stator pole will be made same pole. So these two poles will repel each other, and next pole, stator pole, is made as opposite pole. So repulsion from previous and attraction from the next rotor will rotate in the clockwise direction. So likewise it will keep on going. So rotating magnetic field is created with the help of power electronic switching circuit. The main concept, the reluctance motor of magnetic field, is depending upon the air gap. Hence, by changing the air gap between the rotor and stator, we can change the reluctance of the motor. So actually we are not changing anything. Due to rotation of the rotor, automatically the reluctance is changing. What we have to create is, we have to just keep on changing the stator poles. So sometime one stator pole will be positive, in the next impulse it will, so positive means north pole, next instant it will be south pole, again north pole, again south pole. So likewise the stator poles are continuously changing. Reluctance is nothing but a resistance to the magnetic flux, opposes the magnetic flux. For electrical circuit it is resistance, and magnetic circuit it is reluctance. So here you are finding the construction of a SRM. So after this we will see the video, and again we will come back to this. So here we are finding number of stator poles are more. So these are A, B, C, D, E, F, sorry, A dash, B, B dash, C, C dash are the stator poles. Same thing we found in case of BLDC motor as well. So three phases are created, and rotor, number of rotor poles, these are called salient poles. They are protruding. Protruding poles are called as salient poles. So here rotor is not having any winding, very important thing. So in case of BLDC motor also we found that on rotor there was north pole and south pole embedded. In this case also you can find out it is A, B, C, D and all these things are written. So the rotor is not having any winding on it. Very important thing, no winding rotor, it is written. and phase winding on stator pole. So all the electricity supply is given on the stator pole. Here we are giving the three-phase supply. That means again the control circuit will be using a three-phase kind of an inverter, and three-phase pulses will be produced as we had shown in case of three-phase chopper. Same kind of thing is there. So this is called as a linear SRM. Okay. And what we are finding is the rotor does not have winding, and stator only carries the main field winding. So field winding means it is creating that rotating kind of a magnetic field. So each winding in the stator is connected in series with the opposite poles to increase the mmf of the circuit. So A is connected with A dash, B is connected with B dash, and C is connected with C dash, and three-phase stator supply is given to the motor. It is called phase winding. So A bar, B bar, C bar, or A dash, B dash, C dash is there. Now stator has inward projections and rotor has outward projection. So you can say that rotor is called a salient poles, stator is called a simple poles. So in switched reluctance motor, the stator and rotor have projected pole made up of soft iron silicon stampings. So all this you are seeing the front view. So such many laminations are actually laminated, such many discs. So this is one disc you have seen. Okay, such many discs are laminated, so it is called laminated. We don't make it a core constant or uniform core. We don't make it because uniform core can have eddy current loss. So that's why one a disc like this is made, and such many discs are stamped together. Okay, if you want a motor is this kind of long. Okay, so the whole big structure of steel we don't make it, not a unit structure. We make stampings. Whatever you are seeing here, a thali jaisa, we make one thali like this, and such many things are stamped together, and each of the discs are laminated. Laminated means जोड़ा जाता है, okay, with some gum, okay, with some adhesive, and that is non-conducting. So from one lamination to the other lamination there is no flow of current, and that's why eddy current is less in laminated core. So this is called laminated core. So in switched reluctance motor, all the if you see DC motor, if you see induction motor, for everywhere the core is not a unit or single unit. It is the lamination of many discs to reduce the eddy current loss. Eddy current increases the heat production, and that increases the loss in the motor. All those things. So we want to avoid that. So in SRM motor, the stator and rotor are projected poles made of silicon stampings. Silicon stamping is used to reduce the hysteresis loss and eddy current loss as well. So poles in the stator will be around 6 to 8. So here we have shown 6 stator poles, and rotor poles are less than that. So if stator is having 6 poles, rotor will be having 4 poles. If stator is having 8 poles, rotor will be having 6 poles likewise. Because if number of poles in stator and rotor are same, there is a big chance that rotor and stator will get locked, because exactly one pole will come in front of another, one rotor pole and another rotor pole will come. So here in this case A and the rotor, you are finding that here the least reluctance path is created. So just in front of A dash, the rotor poles are situated. So you are finding that this is the least reluctance path. So flux lines will be flowing through A, then it will flow through rotor, then again rotor, it will flow through A dash. So this is the least reluctance path. But the other pole of rotor, I think BB, okay, this is in between BC and B dash C dash. So here the reluctance is more. Hence, if given proper pulses, this rotor will rotate either in clockwise, it will go towards B, or it will go towards C. Exactly in between it is there, so it can go in any direction. So either we can make the rotor clockwise rotation or anti-clockwise rotation. So just give one pulse, and suppose this B is rotating clockwise, and it will come in front of B dash. So in this case, if this rotor rotates one step in clockwise direction, so this BB rotor poles will come in front of capital B dash stator pole. So in that case, this AA will shift. AA will come in between AC and A dash C dash. Okay, and then in the next instant again we will trigger CC dash, so that this A dash will come in front of CC dash. So likewise it keeps on going. So continuously we have to keep on changing the A, B, C and A dash, C dash, B dash poles. So sometime it is north pole, next instant it is south pole, again it is north pole, again A is south pole. So likewise we keep on changing, so that this rotor keeps on getting that carrot. It will try to catch that changing of pole, and this will keep on rotating. And the rotor is actually rotating at very high speed because we are changing this A, B, C or A dash, B dash, C dash poles very fast. Because we manually are not doing it, it is done by electronics. So whatever monostable multivibrator, astable multivibrator, pulse generator you have studied, those kind of things are actually used to give the stator pulses. So the poles in stator will be around 6 to 8. So like this, by increasing the number of poles, we can get low angle of rotation. So here the angle of rotation is kind of 60 degree because 360 is totally divided by 6 poles. So for each pulse, there will be a 60-degree movement of the rotor. A position sensor. So whenever the pulses are supposed to be given to any of the stator phase, at that time the DSP controller. So in this case also the same thing. There is a DSP controller who is generating the pulses for the stator. So DSP controller should know exactly where the rotor is at present. So depending on that, the DSP controller would decide which stator pole I should give create N and which stator pole I should create S. Okay, North pole and South pole. So for that, knowing the position of the rotor pole is very much important. So hence there is a position sensor on the rotor shaft. It determines the rotor position at any moment and feeds back the information to the control circuit. So the control circuit always collects the rotor position information first. Yesterday we have seen in case of Bldc motor also. So there were three inputs to the DSP control circuit. First, the demand or set point. So how much torque is expected, how much torque the driver is demanding. So that torque is converted to current first. So that was the set point that was coming at the input side of DSP. In this case also the same thing is happening. DSP is digital signal processing. And second input was coming from what is the current stator current that is given. What is the present stator current which is rotating the BLDC motor. So for all these three phases, how much are the currents that is being given to the stator coil, that thing was that input, and how much power input we are giving to the BLDC input, that information was coming to DSP. And third thing was another input feedback, which was what is the rotor position at present. Okay, depending on that, again in BLDC also we are doing the same thing. We are always trying to rotate the rotor by one step. Okay, and in the next step again the control is changing. So we are keeping a caret in front of the rotor. That is okay. If now you are under N pole, as soon as N stator and N rotor they aligns, there is a S which is generated in the next rotation. So as soon as the rotor N finds that there is a S to the next, because opposite pole attracts, so rotor N would be attracted towards stator S. So as soon as that N goes to the stator S, we again change that stator S to stator N, and next stator pole is again created as S. So likewise this N rotor will continuously try to catch the S of the stator, and we change the rotor poles by that electronic controller. So DSP processor is having three inputs. One is how much is the torque expected, how much is the current being given to the stator pole, what is the position of the rotor. So here also the same thing happens. That is, the sensor is mounted and control circuit always collects the rotor position information, and after that it generates what is the control strategy. So here you can find in the right side what exactly is the this list reluctance or switched reluctance. So we are actually switching the pole. So here you can find the arrow direction is going to be different. So as soon as it is coming in front of one pole, least reluctance is happening, and as soon as that is happening, we are changing the next instant. So you can say that whenever it has become lighter colored, suppose this is becoming N pole. So you can see that this N pole is rotating, and dark color stator pole, let's say it is S pole. Okay, so that N is changing. You can check N, 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 likewise. So the whole the six stator poles are becoming NS, NS, NS alternatively, and you are putting a caret in front of the rotor, and rotor keeps on rotating like this. So SRM has two types. One is singly salient, one is doubly salient. Singly salient means either stator is salient or rotor is salient, or doubly salient means stator and rotor both are salient poles. Stator and rotor magnetic circuits are laminated to reduce the core losses in both the cases. SRM is constituted by a stator which is with concentrated windings disposed around pole cores and the rotor composed by salient poles free of windings or magnets. So this is very important thing. There is no magnet, or there is no winding on the rotor. So normally each stator phase is composed by a couple of windings diametrically opposite. So this A dash, then B dash, and then C dash. Okay. An Srm configuration with 6 stator and 4 rotor is shown here, and this is how the thing is rotating. Now I can make this rotor rotate both in clockwise direction as well as anti-clockwise direction. I have to just change the sequence of pulses that is being given to the poles. So this is another advantage. Just by little programming of the DSP controller, just by changing the pulse inputs to the stator coils little bit in the opposite direction, I can make this same rotor rotate in clockwise as well as anti-clockwise direction. The motor works on the principle of variable reluctance. It is already mentioned. So this means rotor always tries to align itself along the lowest reluctance path. So this is what it is doing. You can check. So if you just track one point, you'll be finding that it is always trying to go to the next pole and in a least reluctance path. And inertia takes it. So as soon as it is aligning itself to perfectly to the least reluctance path, then also why does it move? Because of inertia. And as soon as it moves, the alignment is disturbed, so that it tries to go to the next best reluctance path position. So like this it goes on. So as we know that the magnetic flux have a tendency to flow through the lowest reluctance path, therefore the rotor always tends to align itself along the minimum reluctance path. So when a stator phase is magnetized, so this is a stator. Okay, stator is having winding. That winding is we can make current flow in forward and reverse direction, and the stator pole will become north sometime, it will become south sometime, N on S. So when a stator phase is magnetized, a closed magnetic field is generated between the stator and the air gap and the rotor. So the rotor will try to align itself in such a way that the air gap between the stator and rotor is minimum. So that is called as least reluctance. The magnetic field tends to minimize the reluctance by reducing the air gap, which creates a rotor movement. Okay, so rotor rotates because it wants to have least reluctance path between the stator pole, air, and rotor. So when a stator pole is aligned with a rotor pole, it is said that they are in position of minimum reluctance. And when they are completely unaligned, they are called as reluctance is maximum. So this characteristic of the motor makes it possible to create a rotational movement of the rotor by magnetizing and demagnetizing each phase in the right position of the rotor. So demagnetizing means you are changing the pole to the same pole. So rotor and stator pole. So as soon as if this is north pole, in front of this the rotor south pole comes. That means perfect attraction. Immediately the top rotor stator pole also we are making north pole. So initially the stator is north, rotor is south. Okay, stator is north, rotor is south. So least reluctance. As soon as the south rotor comes in front of north stator, what we are making is we are making the stator pole also as south pole. So now they are opposing, because initially the stator was north, below was south. Now as soon as least reluctance, we are making the stator also south. So the south pole and rotor south pole, rotor is repelled, and whatever is the before, whatever is the stator pole, that we make as north. So likewise it keeps on going. So demagnetizing means that opposing, magnetizing means they are attracting. So there's a functioning of SRM DSP based controller. You are finding this the DC input. So for every of these things, input is DC. We don't have a AC, but this motor runs with AC. Okay, so there should be a converter. Actually, this is not called as converter. This should be called as an inverter, because DC has to be connected to three-phase AC. Okay, so this is the SRM drive. It is having rotor and stator. Stator is getting the three-phase supply. So this converter circuit actually takes DC. So we have seen in case of three-phase that DC chopper, that PWM thing. So that is very important thing. You just prepare. In case of DC, we had two controls. Sorry, not DC. I'm sorry. In case of induction motor, there was a three-phase PWM controller. Okay, so there the same thing happened. That DC from DC supply was coming to a converter circuit, and there we generated PWM. But in this case, we are not doing anything like that. This is a digital controller which is having input from the SRM motor speed sensing. So it is finding motor speed sensing and rotor position sensing. So one more thing we can add here, motor speed sensing and rotor position sensing. Both the things are coming to a digital controller, and depending on that, digital controller is deciding which phase is to be given which kind of supply, so that it becomes north pole or south pole. So accordingly, the gating or reference signal is given to the converter circuit. Converter circuit makes A, B, C, three phases are there. Okay, which phase has to be given what kind of supply? So if you are giving A phase positive first, then maybe A phase becomes north pole, and B phase negative, then B phase becomes south pole. So depending on the position of the rotor, digital controller comes to know it, and it gives that gating signal to the converter circuit. Converter is nothing but a inverter which converts DC into three-phase AC, and this converter circuit produces the pulses accordingly, which are given to the SRM, and this process is a continuous process. Okay, every instance it is going on. So frequency maybe 1 kilohertz or something, or more than that. So depending on that, motor keeps on rotating very fast. If you are giving one pulse at a time, then the motor will rotate like this. It will rotate like a stepper motor in jerk, 1 degree, one step, one step, one step, likewise. No, it doesn't happen like that, because this digital control is continuously giving the gating signal to the inverter, and inverter is continuously giving the whatever is the stator energizing pulses that inverter is generating continuously. So it's a very continuous process. So we find that the motor is rotating in a continuous method. So the DC input is connected. So this DC input coming from the battery of the car. Okay, so charging of the battery of the car is very important. So DC input is connected to the driver or converter circuit. Actually, it's an inverter, and the output of the inverter is connected to the motor. The rotor sensor's feedback wire is connected to the controller circuit. So rotor sensor is connected to the controller, and it provides the position of the rotor with the reference to the reference axis. And then accordingly, digital controller decides which phase has to be given which supply, so that we are creating north pole and south pole, and the converter circuit, converter topology does that. So finally, the controller collects all the information, and based on that, reference will be given to the stator. So that is the gating or reference signal. Also, the controller monitors the motor current to protect the motor from the internal and external faults. Okay, so controller is having one input from the state rotor pole. What is the position of the rotor? And second thing, from ABC phases. So from these three phases through current sensor. So yesterday I had talked about that CT-PT sensor. So from CT sensor also, you can bring how much is the current going to the SRM phases. So that is another set of feedback you can bring from the ABC to the digital controller. So that is what they are speaking. Below I have shown you the diagram. So this is what, so two diagrams are shown. Left side, whatever diagram is there, it's a 6 pole. You can find there are 6 stator poles. Okay, so these are the 6 stator poles, exactly the diagram which is shown in the moving diagram which was shown in the previous slide. Same kind of thing is given here, and this is what the overall thing looks like. And in between, so these are all stator poles, stator coils, and all these things are shown, and there's the overall combination. So SRM is run by reluctance torque. So whatever is torque produced because of this least reluctance kind of thing, this is called as reluctance torque. It is also called as a variable reluctance motor. The property of a magnetic circuit of opposing the passage of flux is called as reluctance, and the ratio of the magnetomotive force to the magnetic flux. So due to the higher efficiency, magnet less operation, simple mechanical structure, SRM is highly preferred in EVs. Now, why did I send that video yesterday in the group, yesterday night? A very interesting video of 12 minutes have been posted in the WhatsApp group. Please check that. Now you will understand that thing full clearly. It is called a SynRM, not SRM. SRM is switched reluctance motor. That is called a SynRM. Okay, and that is used for Tesla 3 vehicles. Okay, so Tesla model was having Tesla model S was the basic model, where they were using induction motor, but in Tesla 3 model they are using reluctance motor, not switched reluctance but synchronous type of switched reluctance. Okay, so that's why that is called as a SynRM, very compact motor designed by Tesla only, and a very unique kind of very highly efficient motor. So what all advantages this thing is having? Higher efficiency, magnet less operation. So whenever there is no magnet in the stator, rotor, nowhere there is a magnet, hence all the losses will be very less, and we are not creating any magnetic field. That's why the field creation is not there. So unnecessary usage of field coil is not there. So it's a very unique kind of motor that they have designed. So please check that. That is a SynRM motor for Tesla 3. And this is a converter circuit of SRM. So you are finding that this is a DC input. So whatever converter circuit is shown here, converter circuit, the same thing I am showing in detail here. So this is a coil, this is a coil, stator coil, whatever is shown here, the coil, okay, whatever is shown here, this is the coil, okay, this is a coil in every a dash b, b dash c, c dash. So what is that? That coil is nothing but this one. So this is a coil, and these are two transistors, which one is in the for the forward path, because pulses are having positive as well as negative. And these are the diodes, which are that freewheeling diode, which was explained earlier to you. So DC input is coming, and this is forward driving, reverse driving. So when this transistor is acting, suppose the pole is getting, so there is a winding in the pole, one is clockwise direction, and both the time, so we are making the current flow through that coil, once in clockwise direction, one is anti-clockwise direction. And we know that whenever current flows in the anti-clockwise direction, that pole becomes north pole. Whenever the current flows in the clockwise direction, that becomes south pole. So how can, so coil is the same on the each of the stator poles, but we can change the direction of the current flowing through that coil, and by that we are creating north pole and south pole in the same stator pole. And suppose this thing is making the current flow in the clockwise direction to the stator coil, so in that case it is becoming south pole. And when this is on, okay, and base of that thing is again controlled, so all these things are having base, so those base are to be switched on and switched off. So there are 6 timing circuit at the base of each of these transistors, and they are actually making the transistor on and off. So if this is the first arm for part phase A, this is the second arm for phase B, and this is the third arm for phase C. And if we name that 1 and 4, these two transistor, this is 5 and this is 3 and 6, and this is 5 and 2. So when 1 and 4, when this 1 is on, 4 should be off. When this 3 is on, 6 should be off. And when this 5 is on, 2 is off. Okay, so this 1, 3, 5 may be there for the positives, that is current flowing in the clockwise direction, and this 4, 6 and 2, they might be the current in the anti-clockwise direction. So whatever is the switching pulses shown, this is given here in this direction, and you're finding that part A first given positive. So let's say positive is clockwise direction, so first part A is becoming south pole, then after a certain time phase B is becoming south pole, and then after a certain time phase C is becoming south pole. So you are finding that they are mutually exclusive. So at any instant of time you will be finding only one phase is becoming high at any instant of time. Okay, so at first instant phase A is given positive, okay, and next instant B is given positive, so this is on and this is off. So there's a very proper synchronization of all the pulses, and this is what is tracked, or this is what is executed by the controller circuit, which is given in the previous phase. So the same kind of pulse, whatever is there, this you can draw in case of BLDC as well. BLDC also, there are 3 phases, the same thing happens. The same phase diagram, switching pulses, can be reproduced in case of BLDC as well. If it's a 6-pole motor, 6-pole stator. Okay, if it is 8-pole, again there is a phase D, and in that case there will come another pulse here. But generally it is multiples of 6 only, or multiple of 3 only, that we find. So if we keep an iron piece in the magnetic field, so this is another explanation. If we keep an iron piece in the magnetic field, though the rotor is like a magnetic piece in the magnet field, or iron piece in the magnetic field. So if we keep an iron piece in the magnetic field, the iron piece will align itself with the stator poles, so that minimum reluctance is created between the stator pole and the ferromagnetic substance, whatever iron bar is created in the field. Okay, so it will get locked magnetically with the stator. So get locked magnetically means this is the stator pole, then it will be exactly, the rotor will be aligned like this, and this is the another stator pole. Okay, and then next one, so this is another stator pole, they will be again energized. So again rotor was like this, rotor will rotate like this. Again then another, there is C phase, okay, they are energized. So whenever it was like this rotor, again the rotor will get aligned like this. So it keeps on going very fast. So the same principle, so what they have said is, if we keep an iron piece in the magnetic field, the iron piece will align itself with the minimum reluctance position and get locked magnetically. The same principle is followed in the switched reluctance motor. The minimum reluctance position of the rotor tries to align itself with the stator magnetic field, hence the reluctance torque is developed in the rotor. So what are the special features? Synchronous operation, that means whatever is the rotating magnetic field speed, that means whatever speed you are rotating the pulses through the stator coils, that is called a synchronous speed. So the rotor will also rotate in the same speed. Okay, so low cost motor due to the simple and magnet-free construction, more suitable for high speed power density applications. What are the advantages? It does not require an external ventilation system. That means airflow and all this thing happens automatically through the stator and rotor slot projections. Rotor does not have winding, since therefore no need to keep the carbon brush and slip ring assembly. So there is no brush, there is no slip ring assembly. Absence of PM makes such motor cheaper price. A simple 3 or 2 phase pulse generator is enough to drive the motor. So whatever pulse we are generating, we have shown here 3 phase pulses. So that's a very simple thing in construction. So 1 or 2 monostable multivibrators will do the job, and perfect timing adjustment is possible. So control is also very simple. So self-starting. Okay, AC single phase motor are not self-starting. Okay, so that is a problem. We have not studied single phase motor, but I have uploaded the video, I think you have seen. But the AC single phase motor or single phase induction motor is not self-starting. It requires some external capacitor or external assembly. But this SRM is self-starting. So some external starting assembly is not required. So this is having very high starting torque without excessive inrush of current. Okay, excessive inrush of current might damage the coils. Okay, but in this case, starting torque is very high and it does not require very huge inrush of current. So if there is huge inrush of current, certain times certain SRMs are there for which very high starting current is required. In that case, that puts a lot of demand on the whichever is the power electronics part. So whichever is the controller power electronics part, huge pressure comes on that if the SRM is asking for heavy current at the starting. Okay. So that thing is avoided. Fault tolerance is not there. That means some small problems and all these things generally does not happen in case of SRM, because construction is very simple. There is no brush, there is no commutator, there is no rotating mechanical part, there is no noise. Okay, so all that's why wear and tear is less. That's why fault tolerance is very high. Phase losses do not affect the motor operations, and high torque by inertia ratio. And the high torque by inertia ratio means with very less amount of weight of or very less amount of inertia of the rotor, then also the rotor can produce very high torque. So inertia is directly proportional to how much is the mass of the rotor. The rotor mass is very less, but generally it is able to produce high torque. So high torque can be produced only by heavy material or heavy rotor. But in this case, rotor weight is very less, but then also it can produce very high torque because of its operation. Why? We will see later on. So high torque by inertia ratio is there, and high starting torque can be achieved. This is there. SRM advantages. Okay, so creates torque ripple at high speed operation. The external rotor position sensor is required. This is a disadvantage. I'm sorry. What is the disadvantage? So creates torque ripple at high operation. So torque ripple means whatever ripple is produced, that actually affects the performance of the motor negatively. So whenever very high torque operation is there, automatically some amount of in a harmonics or ripple is getting introduced in the system. So external rotor position sensor is required. Obviously it is there because the DSP has to know which phase has to be converted to north pole and south pole. Without that, the whole operation of the motor will be in jeopardy. That's why always there is a rotor position sensor which is required. Without that, not possible. Noise level is high. At a higher speed, the motor generates harmonics. So harmonics is actually related to the ripple. So larger side of capacitor reduces the harmonic. So here, problem and solution both are given. That at higher torque, higher speed, there is a harmonics generated. So whatever is the base frequency, we find that multiple frequency of that is produced in the electricity of the motor, that means stator supply. So if we put higher value of capacitance, that actually reduces, it's a filter kind of operation which reduces the higher harmonics. If PM is absent, as PM is absent, high input current is required for the motor operation. It increases the converter kVA requirement. Okay. And what are the applications? Applications you are finding: general purpose industrial drive, application specific drives like compressor, fan, pumps, centrifuge, domestic drive, food processor, washing machine, vacuum cleaner, electric vehicle operation, aircraft application, servo device, etc. So these are all about SRM and its control. So how to control the speed of the SRM motor, that is switch reluctance motor, and what all are the advantage, disadvantage, special features. KVA is kilovolt ampere, Siddharth. Kilovolt ampere, because there are three kinds of power. One is active power, which is given by watts, which one is called as reactive power, which is called as volt ampere. So volt ampere is the reactive power, and apparent power. So active, reactive, and apparent. VI cos phi, VI sin phi, and VI. Okay. So whenever we are talking about transformer, we give the power as VA, volt ampere. It's a reactive power. Okay, so this is a converter control circuit, control pulses. I'm going back. This is the controller circuit. Okay, so there's a controller circuit getting pulse. This circuit actually in detail in discrete components, and here the overall block schematic. So read the question carefully whether control block schematic is asked or controller discrete circuit component is asked. So this you have to understand. So this is with a discrete component. What is the circuit in detail? This is a getting pulse, and before this one is the schematic. And then this is the principle how it operates. And this slide is very important, where they're explaining about all the stator phases, rotor phases, and everything. And now I will stop this presentation and I will show you a video. As long as you are there, please listen to this video. Switch reluctance. I'll just play a video. Just give me 2 minutes time, and just let me know whether you are able to listen to the audio or not. So in this video, one mistake they have done, as per my knowledge, that is they have kept the rotor and stator pole same. I don't want that, because what we have found is, so this is something the person is explaining and it is in Hindi. I'm sorry if people are very not conversant with Hindi, they might be finding a little difficult. Is the video visible? Is the video visible? Somebody just say yes or no. I think it is visible.
Yes, sir.
It is visible. See, if you want to leave at 10:55, you please leave. This video link will be uploaded. Whatever I had to explain, I have explained. And this video will go on with the video link. Then my lecture link, whatever I upload, it will be going with that. As well as this video link you can find in YouTube. I'll give the link. You can check it because time is we are a little late. But those who are staying, they can. Here the main problem he has created is he has shown 4 stator and 4 rotor. The rotor pole and 4 stator pole. So this I don't like, because the stator pole should be more. Stator pole should be 6 and rotor pole 4 is okay. But this fellow has used a very unique kind of explanation method. I will show you that. So I will run the video a little. So whenever you are drawing, you please draw 6 stator poles and 4 rotor poles. That will do. So he is using a single phase SRM, but we have used a 3-phase SRM, because 3-phase SRM is having higher power capacity, so the phase does not matter. The single phase SRM, whatever they are using, the single phase he has split into 2 phases. We can find here, and that 2 phase is creating the rotating magnetic field. Now this is his unique method what he has used. So paper disc he has created. So this is north pole, south pole, and north pole, south pole he has shown, and now he is going to show the stator. Now he is going to rotate the whole stator and rotor part. Just check what he is explaining. So initially, whatever pulse we have given, the top stator pole is created as north, and this stator pole is created as north, and opposite is south. If this is north, automatically the bottom becomes south. Okay. So as this is a single phase switch reluctance motor SRM, in that case, only two pairs of north and south are created. If you are using three-phase motor, in that case, three pairs of north and south are created. But this is the basic fundamental. You just understand when you explain in the exam or something, please show by three pairs of north and south. Now just concentrate. Rotor N would try to come to the stator S because that is the law of attraction. So it will rotate in the anticlockwise direction. This is happening because of least reluctance part. So I think whatever explanation is given till now, this is enough for you to understand how exactly the SRM is rotating. Now he is actually explaining the problem of interlocking. So we are not going to see the problem of interlocking immediately. Only whatever is the function of SRM, if we know that, that is sufficient for us at present. So this is about SRM, and this is about how the switch reluctance motor is rotating. So I will post this video lecture video as well as whatever links I have prepared all the slides from, that also I will post. And this concludes actually the module number 2. So now you have to write the OBA, and now I will give you the question set for module number 1 and module 2. So next day, that is Tuesday, we will be logging in with the same link, and we will start with the module number 3. So that's all from my side now. Thank you.